Welcome to the AI in Manufacturing podcast here on Industry 4.TV. I'm your host, Kudzai Manditereza, and today we've got a very interesting topic here of discussion. We're going to be talking about CDOT AI code or smart AI code for advanced industrial traceability. And my guest on this episode to help us unpack that is Serra Tuzcuoglu, who is the CEO and co-founder of Cosmodot. Serra, it's great to have you on the show. Welcome.
Hi, hi, Kudzai. I'm happy to be here. Thank you for having me.
Awesome stuff. All right, maybe to kick things off here, could you start by introducing yourself to our audience and telling us a bit of a background about how you got to form your company?
Yeah. I am Serra Tuzcuoglu, and I'm the CEO and co-founder of Cosmodot, creators of CDOT AI code and CTRACE in-factory tracing methodology and platform. People actually always kind of asking us where did the idea for CDOT code even came from. So the answer is kind of funny because we are just two people with my partner obsessed with turning analog things into digital ones. So before CDOT, my co-founder and I built a company around handwriting digitalization. That technology is still used today, from verifying bank checks, signatures, to traffic tickets, and even in city government paperwork. So it all works using patterned paper and smart pens with intelligent character recognition. So I still love this smart pen technology. It's still amazing. If you followed it, Kudzai, it's you probably saw that this year's CES, a 10 camera pen was named one of the top most inspiring products. But back then, we realized we were holding on to something like a pattern that could become a new code for the physical world. So in 2020, we invented CDOT AI code and the CTRACE methodology and founded our company Cosmodot that same year. So COVID had just hit and manufacturing was slowing down, and we were dying to test our code in real production environment. So we started reaching out every plant director, every R&D director we could find, testing CDOT on printing, tires, metal parts, anything you could get our hands, anything that we could get our hands on. And so one day, I think it was the turning point, and one of the world's biggest home appliance manufacturers reached out, and they couldn't trace parts that went through enabling and high heat processes. So they said, if you can make this code still read after that, then definitely we'll use it. And I think that was the beginning. After months of work in the factory, getting our hands dirty and proving the concept, CDOT AI code was born. So now we can launch CDOT at any factory in the world without ever stepping foot inside the factory floor. So no need to visually inspect the factory floor. We make part and process traceability 100% accurate, fully remote, and even in the most extreme industrial environments. And we bring part visibility to the factory floor.
Awesome stuff. So yeah, I mean, let's start by setting the stage here on the traceability challenges that are currently faced by manufacturers. Can you walk us through how manufacturers typically use barcodes for traceability, and what limitations arise from that approach, and the broader business impact that arise because of that?
Yeah, sure. Uh, Fundamentally, manufacturers rely on barcodes. So typically marked or printed 2D binary codes, as you said, to track products alongside the production line and ship them. So while this sounds like it should provide full traceability, in reality, it doesn't. Why? Because these codes are usually applied at the very end of production process, right before packaging, or even external packaging for shipping. So what happens upstream at the heat, pressure, stretching, shot blasting, treatments, coatings, paints, none of that gets tied to the product's unique identity. So I'm not talking about the average heat treatment values applied to the whole batch. I'm talking about that item specific heat treatment value of that time in that cycle, and applied to that specific product in that batch. So you're essentially flying blind for most of the life cycle. But even when you try to mark earlier in the process, most 2D codes may not survive. So they fade, scratch off, become unreadable after steps like casting, heat treatment, e-coding, or shot blasting. So at that moment, you need the data most during the transformation. It's simply not there. So from a business perspective, that means less accountability, more scrap and scrap related costs, more quality escapes, lower supplier scores, and I think in some cases, massive returns. So in factory traceability is one of manufacturing's nastiest problems, but you can improve what you can see. And without end-to-end traceability, you lose visibility to your own production.
So, I mean, you've developed a technology, as you mentioned in the introduction, C.AI CODE, which basically addresses many of the challenges that you've just raised. Can you maybe just give us a more formal introduction into C.AI CODE for our audience, and sort of like talk to us about how that sort of like differs, or that is a better approach to traditional ways of traceability?
Yeah, yeah, sure, absolutely. So here's the thing. Traditional 2D codes work in a very specific way. So they are mostly based on black and white blocks arranged in patterns. So you know it from the shape, right? And think of it like a Morse code. So two black blocks, one white space, that pattern equals to one. Two black blocks, two white spaces, that may be zero. Or so it's basically a time domain binary system built out of visual contrast. But the thing is, and this is key, the moment that black and white contrast is disrupted, the code is under risk of being gone. So there is no regular layer of information. If the pattern recognition, if that pattern gets faded, distorted, the system can't decode anything. So now some traditional codes try to fix that with error correction. So if less than 30% of that code and only in specific spots like it is damaged, the system might guess and what was there and reconstruct it. But then that's the hard limit, like 30%. So go beyond that, the code might fail. But CRAT is actually totally different. So we didn't build it with black and white blocks. We designed CRAT as a frequency-based code. So instead of reading a visual pattern, our system detects the frequency signals embedded in the structure of the code of the part. So that means even if the surface is shiny, scratched, or covered, or still CDOT still reads. So we are not decoding based on pattern. We are reading signals, real physical signals. So that's why CDOT survives the harshest manufacturing processes and finally delivers the true end-to-end traceability. So let me show you something here. So I take a brake disc and run it through heat treatments. So if I line up like 100 of the same discs side by side and take a photo, each one shows a different reaction. So some have as 80% damage, like here you see some of them are visible, others 90%, some may 60. But think about it, the material was the same. They all went through the same heat treatment machine, and look at the variation in interaction, look at the variation in the code. So we built a decoder that can read even the worst cases of this code in frequency, and honestly, even the worst of the worst can still be decoded with AI.
Yeah. So that's precisely what I was coming to, because you've got this C.AI CODE, and I'm curious if we can dive a bit deeper into how exactly C.AI CODE technology works, particularly why is it referred to as AI CODE?
Yeah, definitely, yes. So yeah, uh, let me give you another example here. So this is a real world example from a cylinder solid rod. Our customer marked with CDOT. So do you know the shot blasting process? It's like surface preparation method that can completely erase anything marked on the part beforehand. So that's exactly where manufacturers typically lose all communication with the part during this process. And of course, that was actually the case before CDOT. So now these four, if you see here the signals underneath, these four different products that went through the same shop blasting machine. So each shows a different level of code visibility afterward. But let's look at its signals. So do you see the faint signal here on the right? So it's almost impossible to catch that using basic if-then logic in code. So out of the signals I picked up, if I have three strong ones and another weak one that barely show up, honestly, if I could just log onto one couple of more signals of those faint signals, I'd be extract the full ID. But if I try to complete the pattern mathematically, just to be sure, the system would fail. Even a difference as tiny as 0.00x in the signal means I can't be certain that it's the right signal. But if you approach it like a traditional 2D code using if-then logic, you'll misjudge whether or not this is the signal you are looking for. But when you actually see it, you know, I know, and I say, hey, this is my signal. Even if it's off by 00x, I recognize the behavior, I recognize the position, I recognize the value of that signal. So that's exactly what we are doing with artificial intelligence. The AI picks up the signal characteristics and makes the right call. So just like that, the ID is solved. But I'm actually being super nerdy here. So I have a very funny example before. If you like, I can show just to understand the AI side better. So
Yep.
I actually recently took a 2-mile road trip in a Tesla and let the car drive basically the whole way. Like at one point, there was this insane downpour and I couldn't see anything ahead of me. And trust me, it was way worse than the video I'm showing here right now and totally blurred night vision. So here's what everyone is asking today. How does Tesla still recognize the road and makes real smart real-time decision in that situation? So normally when I'm driving, my brain is doing some image processing. So that's a tree, that's a person, and doing some behavior based on my previous learning. This road might be slippery, a cat could run out, or better slow down, right? But Tesla doesn't just slam the brakes. So because the water hits the windshield, so the water isn't blocking its ability to understand the road. So the cat hasn't jumped yet and it's still safe. But if Tesla operated in the time domain, purely mathematical formulas, that water would block its perception. So it would fail, just like some traditional 2D codes might fail when the surface gets really messy or distorted. So, but when CDOT AI code doesn't actually work like that. It's recognize the signal like Tesla does to the road, and even the surface is noisy, CDOT AI sees through it. So it picks up the signal, says, this is my signal, and keeps going. And just like the production continues, just like driving continues. So that's basically how we play with AI, even to decode the worst of the worst code.
That's super interesting. So, now when it comes to manufacturing or industrial sort of like operations, can you share some examples where C.AI code is being applied today, and what are some of the promising use cases that you are seeing across other industries?
Yeah, thank you for bringing up this question because it's I mean if you're into very much manufacturing, it's if you're having problem, you can basically see, okay, yeah, I can use this code here. But I mean, when we look at in overall general real world applications, like we are seeing CDOT being used mostly heavily in industries like aerospace, automotive, and casting and forging, defense, iron and steel, electronics, and semiconductors. And that's because these all are the sectors where parts go through intense surface treatments like coating, plating, painting, heat treatment, shot blasting, you name it. So and not just one type of, it doesn't have to be one type of surface. It's like we're talking about everything from soft materials to hardened metals and even mixed material components. And there are some unexpected examples across sectors which I like to show here. We can take a look at these. And the first one is, as you see here, military tank body. So this tank, the green, underneath the green pictures, we have our codes. So you can see that it's for the traceability of the whole sheet metal from coil stage, including the painting of the code. So we can read through paint, so you can basically trace all your metal sheet parts in your production. And beyond that, after that, you can still decode. Even though it's the tank, it's in the field now, dust comes over it, over paint, and you can still decode and you can still trace the thing. And the second one, interesting one, is, so it's printing cylinders, like the ones you use in offset, or offset kind of printing for packaging. So this kind of cylinder is like, the manufacturer had lots of cylinders and going like lots of rolls with paper, producing packaging. And this application actually provides, if they still need, if it is good time for the maintenance of this, how many cycles I have produced these rolls of paper. So as you see, it's amazing that this code, from wear out and use, it becomes rusty, it becomes painted all over. So you can still track if your roll and your packaging process through that, because the code is still there, it still reads. You can still track your inventory if it's not on the line but in the stocks, so you'll know which dates you use this packaging cylinder, for what reason, everything. The next one is I like this example because in this plate heat exchanger, there's almost no place like flat or even. It's all uneven surface, very rough. So where would you put a traditional 2D code? Most probably nowhere, but it doesn't matter. Now with CDOT, you can basically apply to anywhere and put identification and traceability to the plate exchangers. And finally, it's an example from copper industry. Copper is so hard material, very shiny surface. And you see here, there's a very little code. It can be even more small. So the little codes we use when you need little cycle time. But in CDOT, little code doesn't mean little data. So it means the small code is the same data with a larger size CDOT. It is not like you get more pixels like in other traditional codes, that you get to increase the data size. Now, even a small code of CDOT can carry the same amount of data, and so you can put huge amount of data underneath, and it works in short cycle times. Yeah, so that was basically the examples I wanted to take you through.
Awesome. Thank you so much for sharing that. Now I want to move on to another topic of AI. So one of the things that you talk about in relation to C.AI code is how it provides solutions to sort of like meet the demands of industrial air readiness, digital twins, and things like that. Could you speak to us how C.dot supports readiness for use cases like AI-based analytics and the creation of digital twins?
Yeah. That's a great question. It's because CDOT isn't just a code; it's a fine foundation for high quality data collection at the part level and from the first moment of production. So most AI quality systems and digital twins rely heavily on structured, accurate, and continuous data. So, but if you don't have the reliable identifier on every part, especially early in the production process, then your data stream is broken before it even begins. So CDOT enables manufacturers to mark parts before any transformation begins, and the code stays readable through all the harshest processes: heat, pressure, coating, plating, and even shot blasting. So that means every part carries its own traceable identity, right? And every process that touches it can be logged. So you start building a part specific, time-stamped, multi-process data set, which is exactly what AI needs to spot patterns and correlations, and what digital twins need to simulate and predict real outcomes. So without the traceable thread, digital twin may become just guess. With CDOT, they become grounded in reality. And there's one more thing, actually. It's like one of the less talked about but increasingly important like advantages of CDOT. It is energy efficiency for AI. So traditional AI 2D codes like require high resolution imaging, so strong lighting, precise positioning, and often like heavy image pre-processing like binarization, thresholding, edge detection, etc., just to make a read attempt. And every single read involves full frame image capture and pixel level decoding logic. So that's a lot of processing and a lot of energy. So CDOT works differently. Instead of relying on black and white visual contrast, it's decoded through frequency domain signal analysis. This allows us to extract the IDs using minimal visual input. So even low resolution or partial signal data is often enough for us. So no need to pristine images or fixed camera setups. And what does this mean for AI systems? It means like CDOT can pass clean signal data directly into industrial AI models, and even at the edge, because the signal characteristics are more stable and less pixel dependent. So inference models can work with fewer computational resources and faster processing times. So and lower energy. This means lower energy consumption. This is especially valuable in environments running on edge devices operating hundreds of read points per hour. So if you think about really big organizations doing everywhere reading of the codes in the facility. So I can take this one actually one step further, because in digital twin applications, where every part's identity and lifecycle data is constantly being synced and updated in real time, like it uses heavy energy image-based recognition methods. That can be a major drain. With CDOT, you get lightweight reads that carry rich, resilient identity signals and keeps your digital twin alive, accurate, and green. So in short, I think we can say CDOT is like less data overhead, more robust signals, and lower energy per read. So that's a big deal when you're operating at scale from a green AI operation perspective.
I mean, a lot of value out of systems like CDOT comes from being able to operationalize it right in a sort of like in a manufacturing environment, and that means that it needs to integrate with other existing systems. So I'd like you to kind of like walk us through what a typical solution architecture looks like, and how exactly does CDOT integrate with existing factory systems and networks.
Yeah, yeah. What makes our architecture really practical is how seamlessly it fits into existing setups. So no need for new hardware or disrupting current systems. So let's talk about deployment first, and we install our software remotely on an industrial PC that's already in use at the customer side. So that's key. We are not sending over new hardware. Most industrial clients already have an HPC in place, and we just use that. So it keeps things very simple and cost effective. Then there is the CDOT laser client software, which integrates with the laser marking system without interfering with its native software. We don't change the way the machine operates. We simply generate the file formats. It can already handle like SVG or DXF, and the system prints them like it normally would. So once the parts are marked, we move to the network integration part. So any camera, really any image capturing device that can communicate over FTP or SFTP can send images to our decoding software, which runs on the industrial PC. So our decoding processes those images and in real time extracts the CDOT ID in just milliseconds. So no delays, no extra steps. And from there, the data can be transmitted to whatever the system the customer is using, MES, PLC, SCADA, you name it. And we're completely flexible on that. So we don't require customer to buy anything new. We work with their existing industrial PC, their existing laser marking machine, and their existing cameras or handhelds. So the entire setup and integration can be done remotely.
Awesome. So, I mean, I think let's talk about now your CTRACE platform specifically. Can you sort of like give us a deep dive on what it is, what capabilities does it offer, and how it fits into the overall solution?
Yeah, yeah. That's very important. When we talk about the CTRACE platform, we are not just taking a visualization tool. It's actually a complete in-factory traceability methodology and platform built to monitor, validate, and protect quality at every step of production. So what makes it unique? It operates in real time. We are refreshing data every 10 seconds across the entire factory and tracking the exact flow of every part. So where it is right now, which station it passed through, which camera or image device captured it, how long it stayed there, whether it waited, moved, skipped a step. At first, it gives you this complete visibility, like turning on the lights in a dark room, but just seeing things isn't the goal. So traceability is actually only meaningful when or if it's actionable. So, for example, let's say a part skips a required station. It could be human error, a system glitch, or something else entirely. Because our platform knows the correct process flow, it detects that this part never went through a critical step. It can immediately flag that. So notify the operator if the customer chooses. It can even stop the line before the faulty part continues. This is huge, I think, in terms of preventing quality escapes. You're not just catching mistakes after they happen. You're stopping them before they become defects. And beyond that, C-Trace connects each part's journey with the data it touches. So machine parameters, PLC values, sensor outputs, everything is locked and linked to the individual part ID. So when there's a deviation in the production values, even a tiny one, you're not discovering it through final assembly or worse. After the part is shipped to the customer, you're catching it in the moment, and the system can act on it. So whether that means alerting the team, that flagging it for rework, or stopping the flow altogether. So it is a smart closed loop visibility layer that makes factories' lives easier, but more importantly, makes it nearly impossible for a defective product to leave the factory. Yes, it helps with root cause analysis when the things are returned back from the customer to the factory, but even better, it's designed so that defects never reach that point in the first place. So as a result, both scrap and scrap related expenses are minimized to an exceptional degree.
Awesome stuff. Now, for someone who's listening to our conversation right now, and they're kind of like wondering what that implementation roadmap could look like in case they want to adopt this technology, can you sort of like outline the key phases of that implementation and workflow, and sort of like maybe speak about how then are you able to scale from one line to multiple lines?
Yeah. So I mean, like one line implementation starts with the setup inside the industrial PC, laser client software to be tied to the laser marking machine, and the cameras being enabled to take picture and send the pictures to the decode. So this is the one line. But when we talk about implementation and scalability, it's there's something people at this point actually they wonder, and especially because people are used to systems where codes are decoded directly inside the camera. In our case, we don't do in camera decoding, so it actually makes the system more flexible and scalable from the customer's point of view. Once it's set up, there's no difference at all in how it works. It just runs and reliably. So once you have a license for our CDOT decode software, you can get started literally anywhere on any industrial PC. It's that simple. If a factory already has a laser marking machine, great. We simply enable the machine to mark and print CDOT codes in sequence, uniquely without altering the native software. If they don't, sourcing one usually fast. Once it's physically mounted and aligned on the line, automation setup typically takes about few days. In more extreme cases, maybe 1 or 2 weeks, but that's rare. Customers can also work with any laser marking automation partner they trust. We are flexible. What matters is we always deliver a full functional end-to-end readable solution. So no half-baked pilots. Once it's live, and teams don't have to think about really readability again, they should say, yes, this is working perfectly. And the best part is the whole setup is designed to scale. So whether you are doing one line or 10 plans, the same software, the same license structure, the same process applies. It's easy to roll out and even easy to replicate.
So maybe to make this even more clearer for our audience, I would like us to go through some of the case studies that you've worked on. So let's start with cast iron traceability case study. I think you did this for a truck OEM supplier. You worked on tracing brake discs from Greensand casting. So my question here is it really possible to to trace a brake disc or a cast iron product before it's even born, while it's still in the just in a sand mold? Can you unpack that for us, please?
Yeah, absolutely. That's exactly what we did in the case study with cast iron brake disc supplier. So we marked unique CDOT codes directly onto sand molds before a single drop of molten iron was poured in. Now, that means the traceability of each brake disc began even before it physically existed. So while this it was still just a shape in a compressed sense, meaning that traceability started not after machining or later steps, but at the mold stage itself. At 2,552 Fahrenheit, when the molten metal was poured in, the CDOT code transferred seamlessly from the mold surface to the actual disk, and remarkably, it remained fully readable. And why this is significant, starting traceability at the sand mold stage allows you to log all the variable mold parameters, things like moisture, compression levels, binder composition, grain size, and more. So these values directly impact the casting outcome and are often overlooked. So by linking these values to the final product via the CDOT code, you gain the ability to correlate defects or performing deviations back to the exact mold conditions. So instead of discovering issues downstream, you're controlling a major source of risk right from the start. It's a proactive way of producing higher quality, more consistent components, and it pushes foundries one step closer to true data manufacturing.
Great stuff. Let's move on to the other case study. So this one is for Ford Motor Company. I think it's for their aluminum LPDC EV battery housing. So first of all, can you talk to us about what was really happening, with their aluminum batch housing line that made Ford Motor Company want to, invest in this new level of traceability in the first place, and then walk us through on what that implementation looks like.
Yeah, thank you. Definitely. The real challenge in aluminum low pressure die casting, especially for battery housing, battery trays, that starts right after castings during the cooling stage. There's a very tight window there, and the surface of the parts at that point is rough, irregular, and shiny, which makes reliable marking extremely difficult. You need to be able to place a code very quickly, and that code has to be small, tough, and consistently readable, despite the surface complexity. And it's not just about marking. It's the product goes through more than a dozen harsh process steps. One of the most problematic has always been heat treatment. I mean, like these housings sit in high temperature furnaces for hours, and that stage has repeatedly been a barrier in the industry in terms of traceability. In fact, there had been made many attempts, like using traditional codes, laser mark barcodes, labels, even RFID, but none of them could survive the full process. Heat treatment, in particular, was the point where almost every conventional method failed. RFID didn't work, the metal body interfered with the RF signal, making it impossible. And even if someone got through with a readable code, you hit another wall at the basket level. Because these heat treatment racks, the baskets that carry the housings, which hold parts in cycles for hours, sometimes repeatedly across days, become a black box because they also go to heat treatment there. You couldn't tell which part was treated in which basket, under which temperature cycle. We see that not only all the parts traced, but now even the baskets themselves are CDOT coded. So you can trace the whole configuration and sequence of treatment. That's actually a massive gain in process control. And here, something that often gets overlooked, even after all of this, all the part has passed final inspection, being shipped and installed in a vehicle. Life still happens. Parts get scratched, coated, exposed to heat, dust, mechanical wear. Traditional codes may become unreadable under those conditions, but CDOT was designed to withstand all of that. So even in the field, years later, you can still identify the part and trace back its full production history. We created resilience in this supply chain system for aluminum low pressure die casting battery housing products.
So I think we have enough time to look at another case study, if we may. I think we'll look at the Renault crankshaft. So I mean, just looking at some of the importance of the crankshafts, I realized that crankshafts are quite important in an engine, such that whenever one of them, or if whenever it is faulty, you can literally scrap the entire engine. Can you speak to us on what exactly you sort of like did with the result with regards to crankshafts for Renault?
Yeah, yeah, you're right. Crankshafts are a really big deal, and they're basically the backbone of the engine. And yes, it's absolutely true. If a shaft is faulty, you often end up scrapping the entire engine, and it's one of the products that's mostly compromised in terms of traceability, and it's one of those parts where a small defect can have massive consequences for the manufacturer. But here's the problem: the surface of crankshaft is not easy to work with. It's textured, shiny, oily by process. It's full of metal chips coming from the production line. Trying to mark and read a code on that kind of surface, it just doesn't hold. the codes either get distorted or unreadable very, very quickly. And that's exactly the challenge we faced with Renault crankshafts. They needed full part level traceability, not batch and not load, but each individual crankshaft. And that traceability had to survive through all the oil and chips covering the code. So they did some investment, but they wanted to carry their line to 100% traceability. So what we did was to implement CDOT codes, which are frequency based, image based, we can not image based, and that can be read under really messy surface condition. The code was applied in a way that it didn't bypass the processes. It didn't say I cannot read, it's covered by oil. So it was still readable at the final until all the way to the final inspection. It allowed Renault to spot potential defects way earlier in the process, long before the crankshafts reaches the final line. In the end, that means less scrap, more stable processes, more crankshafts, even more engine motors. So that was a tied up bottleneck in overall, which we find a solution with CDOT.
Great stuff. Yeah, so I mean, another topic that I want us to sort of like address here is fair and fine. We've got this great technology, but in my experience, one of the biggest barriers to adoption of technology or AI, in specifically, is really the resistance to change, right? Where organizations are saying, okay, we already, why do we need to change the infrastructure that we have in place? What advice would you have for manufacturing leaders who are sort of like looking at this, wanting to adopt this, and exactly how to sort of champion this within their organizations?
Definitely. I mean, in the organization, yeah, we have been really lucky. Some, of course, some change resistance always is there. It's like, but in general, it's like our thing is like very much taking attention. So we are lucky in terms of we get to set a meeting really quickly because I mean, like last 2D traditional code was came here like 30 years ago. So hey, what's this one, and what can I do with it? So we are lucky in terms of getting the meetings and they ask questions. So the critical thing that usually plant directors, R&D directors, plant managers, head of advanced global engineering teams, digital transformation teams, they were the ones, yeah, truly pushed for the adoption. So these roles actually can recognize the value of deep traceability on and drive the implementation forward. For the teams, like engineering teams, I think it's critical to show the value, like in how many. I mean, like what percentage of scrap will I avoid this if I run this with CDOT in a year? It's very critical to monetize and being able to make it visible in terms of the value to be accepted. Otherwise, yeah, you have to show it, and otherwise it's like, oh, why am I going to change my structure? I've been compromising it, like, okay, so 40% of this line doesn't read. Sometimes I have very much problems with code reading, but I mean, like, it creates lots of losses, right? The operator comes, and then they check for the ID, what was it, and then how it gets so much time confusion, and then you get to lose the connection between the root causes, the values that you produce that specific product. If I mean, like, if something happens that the product comes back from the supplier, they can charge you up to like I had this faulty product. I don't know how you produced it. I don't have the values, but I will send away what you produced even 3 weeks before. So yeah, so this is I think this is the loss that's happening. and that's being compromised. With CDOT, it's all these things could be avoided. It's important to put this financially, to calculate, work with finance teams, and to take out to bring out the value financially.
Yeah, so I mean, as a conclusion here, as a tradition on this podcast, I normally ask our guests to, sort of like give us a prediction, or rather where they see the future of AI in manufacturing in the next 2-3 years. Maybe in your case, where do you see things going as far as traceability is concerned? What's your ideal picture of where things are going in the next few years?
Yeah, I can give you some nice couple of examples, like just for the image wise, like in a factory robot, just doesn't have to be checking the whole thing with a mounted camera. It could be the eyes of robot. It could be just checking the codes on the parts and seeing seeing that at that moment, not checking a software or platform at that moment, the history, what happening behind, and then the same codes with products going to consumer, and then as we like ask things to chat gpt, and people just look at the product, they scan the code either with glasses, I mean, like, or with devices, they can interact with the code. Okay, so they can go to the history of everything's going on. So I always say that. So there was a moment that the textile industries, everything started sharing, like, okay, my sustainability values, I use this much water, this much energy producing this shirt for you. So it is coming to a point that okay, I'm a father, I'm gonna buy a car for my son who just turned 18. So which one of the metal body is more safe for? What's the parameters? Can you show me that? Now it's supplier and OEM trying to get visibility and more process values from each other. The consumers will be asking them for. So then codes with talking directly with AI, who knows the production parameters, everything will be connected to even to the knowledge of the consumer. So we will be more connected, more green in terms of AI and codes, I think.
Awesome. That sounds really interesting. So yeah, we will provide links to your website, your social media channels, and all the relevant material that we discussed here. But in case we have got something that we didn't talk about here on this show that we may have missed, you want to say to our audience?
Well, first of all, Kudzai, thank you so much for letting me nerd out on this topic with you. And it's not every day that you get to go deep in something like in-factory traceability. So I genuinely appreciate the chance, and I hope you enjoyed it as much as I did. And also a huge thanks to the listeners. If traceability is something that they want to hear more, they can have questions. If they're stuck on some of the nastiest challenges on your line, don't hesitate to reach out, please. This stuff can feel like a dead end sometimes, calling lots of laser marking providers, lots of camera producers, buying a very I mean, like, putting more light to the system, and it can take years. I've seen examples like this. Solution might be literally at your fingertips. Don't hesitate to drop us. You can visit us at www.cosmo.com to book a demo, or just shoot at us a note at info@thecosmodot.com. So me and someone from our team, we would be happy to help. And if you're likely, I mean, you will be likely to start seeing answers much faster than you think. And thanks for the great conversation.
Thank you so much, Sarah, again for coming on to the show and for sharing your deep insights with our audience on this important topic. I really appreciate your attendance today. Thank you so much.
Thank you. Thank you. Take care.